Mathematicians have always been interested in prime numbers, and that's partly because prime numbers are the building blocks of all numbers. So what do we mean by that? Well, if you take a non-prime number like 20, for example, 20 can be written as 10 times 2, but 10 can be written as 5 times 2. So this becomes 5 times 2 times 2, and we say that's a prime decomposition of the number 20. And it turns out you could do this for any non-prime number. If you take the number, say 34, 34 is 17 times 2, and 17 and 2 are prime numbers in the same way that 5 and 2 are prime numbers. So that's called the fundamental theorem of arithmetic, and it's a really important result in number theory. And these prime numbers are interesting for lots of reasons. In the modern world, we use them for internet security because they're so difficult to calculate with, and they allow us to make secure connections online and stuff like this. But mathematicians have been interested in them for a long time, and one of the questions that naturally arose is, are there a finite number of prime numbers, or do the prime numbers keep going on forever? It's been difficult to find a distribution method. They don't just appear regularly at regular intervals in the numbers, they appear kind of randomly. So if you start looking at the prime numbers, we've got the set of prime numbers here, starting with 2, so 2, 3, and then 5, 7, 11. And the question is, does that go on forever, or does it stop at some point? And that's what we're going to explore in this little video. So we're going to make an assumption that this does stop at some point P, and because we've ordered our set of prime numbers, they're getting bigger, so we can say that P is the largest prime number. And we're going to play around with the implications of that. So there's a few things we're going to need for this. So one thing, just to go back to this little sort of definition here of the prime decomposition, notice that, so 25 is 5 times 2 times 2. That implies that the numbers 2 and 5 divide perfectly into 20 with no remainder. So 2 divides into 20, and 5 also divides into 20. Similarly here, 2 and 17 divide into 34. So that might seem like a trivial thing, but we're going to need that later on. So we're going to start working with this by doing a very strange thing, which will seem very strange at first. We're going to construct this number q, and q is going to be all of our prime numbers here multiplied together. So 2 times 3 times 5 times 7 times ... blah blah blah, all the way up to the number p, and then even odder than that, we're going to add on the number 1. And this is going to help us explore whether there are infinitely many prime numbers or a finite set of prime numbers. In other words, a largest prime number. So there's two scenarios with this number q. It can either be a prime number or a non-prime number. That's the only two options. So let's start working up the first scenario where q is a prime number. So q is prime. Now keep in mind that what we're trying to achieve here is to say that, hey, if we've got this set of prime numbers, with p being the largest prime number, can we find another prime number which is larger than p? If we can find one which is larger than p, so a number like here, then we could repeat the process and say, hey, there's one larger than that and one larger than that. The implication of that would be that the prime numbers go on forever, so there's infinitely many prime numbers and there's not a largest prime number. We can't do that by exhaustion, because if you start to list the prime numbers, if there are infinitely many, then you cannot list infinitely many items. So if you got the first million or billion or trillion, then it doesn't matter because you've got infinitely more to check. You can't just draw a general conclusion. So we need a logical argument. So let's say that this number q is a prime number. Well, in that case, we're kind of done, because clearly this product here, if you multiply these all together and then add on 1, clearly that number is bigger than the number p. So in other words, we can say that q is greater than p. So we've established a prime number which is bigger than p. So we found a bigger prime number. So that kind of meets our criteria. That's sort of the trivial case. The less trivial case is if q is a non-prime number. So if we can start with the assumption that q is a non-prime number and somehow show that we can still find a prime number bigger than p, then that will prove that there are infinitely many prime numbers, because we'll have said in either of these two, the only two possible scenarios for the number q, both cases lead to a prime number bigger than p. So where can we go with this? Well, we can go back briefly to this idea over here. So if you take a number like 20 and realize that its divisors are 5 and 2, it's prime decomposition. But if you then take the number 20 and add on 1, kind of like we're taking our number here and adding on 1. So if we take 20 and then we add on 1, obviously that's going to be 21. Now, does the number 2 and the number 5 divide this new number, 21? In other words, if you take a non-prime number where you've added on 1 on the end, are the prime divisors still divisors of the new number? Well, clearly not. 2 does not divide 21. 5 does not divide 21. Similarly over here, if you made this 34 plus 1, which will give you 35, 2 does not divide 35, and 17 does not divide 35. So what that tells us is that none of these prime numbers, 2, 3, 5, 7, blah, 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 all the way up to p, none of those prime numbers are going to divide into this number q, just in the same way that 2 and 5 don't divide into 21. So where does that leave us? Well, that leaves us thinking, well, okay, that's maybe fair enough, but we know that q is a non-prime number. And by the fundamental theorem of arithmetic, non-prime numbers must have prime divisors. So we've established then that 2 does not divide into q. We've established that 3 does not divide into q. We've established that 5 does not divide into q. None of these divide into q, so all the way up to p does not divide into q. But we know that there must be a prime number that does divide into q, because we're assuming that q is a non-prime number. But it is not in our list of prime numbers. Well, the only possibility then from this would be that there must be some other prime number which is not in our list. If there is another prime number which is not in our list, assuming that these are all the prime numbers up to p, let's call that prime number p1, then it must be that p1 is a prime number which is bigger than p. That's the only possibility. If these are all the prime numbers up to p, none of them divide into this number q, but q is a non-prime number, then by definition and by the fundamental theorem of arithmetic, there must be a prime number which does divide into q. The only possibility, therefore, is that it's a number larger than p. That means that regardless of whether you assume that q is a prime number or a non-prime number, both scenarios lead you to finding another prime number, q in this case, p1 in this case, which is larger than p, which was assumed to be the largest prime number. So in other words, you can always find a larger prime number. Therefore, there are infinitely many prime numbers.